Hey Algebra students, in this video I'm going to be talking through Chapter 8, Lesson 3 of Jacob's Elementary Algebra. And we're going to start by going over the new concepts and then walking through Set 3 of the homework problems. So I've got this up on the board still. Scientific notation is when you put a number in the format of a times 10 to the power of b. And the rules for a are that a has to be some number that is at least 1 but smaller than 10. And then b has to be an integer. So 10 has to be raised to the power of a whole number like 0, 1, 2, 3, 4, or its opposite, negative 1, negative 2, negative 3, negative 4, etc. Because that's what integers are, is whole numbers and their opposites. All right, so that takes us to this lesson where we're going to start dividing exponents rather than simply multiplying them. So to review, if I have the first rule of exponents, that says, the first law of exponents, if this is not already in your math dictionary, please put it there. This one says, if I have x to the power of a times x to the power of b, I can add their powers, and I get x to the power of a plus b. So, for example, if I had x squared times x cubed, it becomes x to the power of 5, 2 plus 3. All right, so now let's move on to the second law of exponents, which is in this lesson. The second law says this. So if a and b are positive integers and x is any number other than 0, then x to the power of a divided by x to the power of b is the same thing as x to the power of a minus b. All right. Remember how I said that when you have a negative exponent, a negative b, as it were, then that's the same as dividing by that power. So I'll do an example. If I have, let's say, 2 squared, or I'll say 2 cubed, divided by 2 squared, then what I'm saying is 2 times 2 times 2 divided by 2 times 2, aka 8 divided by 4. What does that equal? That equals 2 to the power of 1, or just 2, all right? So 8 divided by 4 is 2, and if I take the power of 3, subtract the power of 2, I get the power of 1. So this second law of exponents checks out. When I divide an exponent by an exponent, if they have a common base, I can actually subtract the power in the denominator from the power in the numerator and get my answer. Okay, so let's do an example that also illustrates that. So if I had 3 to the power of 4 divided by 3, what do I get? First of all, what's the power of just regular 3? Well, that would be raised to the power of 1. Because any number to the power of 1 is just itself. That's an important thing to know. So now I could actually solve this by subtracting the power in the denominator. So I could say 3 to the power of 4 minus 1. And that would be, 3 cubed. And I could figure this out too, mathematically, because what's 3 to the power of 4? 3 times 3 times 3 times 3, that's 81. And if I divide that by 3, I get 27. And 27 happens to be 3 cubed. 3 times 3 times 3 is 27. So yeah, it checks out. All right, so now they're going to very quickly take you to the third law of exponents. The third law of exponents. So if a and b are positive integers, then x to the power of a raised to the power of b is going to be the same as x to the power of ab. So here, if I take an exponent and raise it to an exponent, I can multiply the powers. So let's illustrate that. Let's say I've got 2 squared, and then I square 2 squared. Well, what's that really saying? That's the same as 2 to the power of 2 times 2 to the power of 2, because I'm squaring it. So everything inside parentheses, if you square it, is multiplied by itself. So 2 squared times 2 squared. And what does that equal? Well, 2 to the power of 4. And I could figure that out 2 different ways. I could say, well, 2 squared times 2 squared, add these powers using the first law of exponents. Or I could save myself some trouble and say, all right, 2 to the power of 2 times 2, 2 times 2 is 4, using the third law of exponents. So that actually works out. And if I wanted to figure this out just mathematically, like fully work it out, 2 squared squared equals, again, 2 squared times 2 squared. And that equals, what's 2 squared? 4 times 4. That equals 16. Is 16 the same thing as 2 raised to the power of 4? Yes. 2 times 2 is 4, times 2 is 8, times 2 is 16. 2 to the power of 4 is 16. So this checks out. I've just shown evidence for the third law of exponents. Okay, so now we're going to do the problem set. But first, I want you to pause this video if you haven't already. Write out each of these laws of exponents in your math dictionary. Because I don't have a big enough board to keep them all up here. So I'm going to erase them, and then we're going to begin. I've gone ahead and written the third law of exponents up at the top so we can refer back to it as needed. So now we're going to go into number 11. So from set 3. Show, as was done in the examples in this lesson, why each of the following equations is true. All right, so 2 to the power of 4 times 2 to the power of 3 equals 2 to the power of 7. What's that an example of? Well, that's an example of the first law of exponents, saying that when you have the same base, you can add the powers. 4 plus 3 is 7. All right, what about the next one? We have b, and b is like this. 2 to the power of 4 over 2 to the power of 3 equals 2 to the power of 1. So that is going to be true because of the second law of exponents, which says that when you're dividing one exponent by another, if they have like bases, for example, 2 and 2, then you can actually subtract the exponent in the numerator's value. You can subtract the denominator from it. So 4 minus 3 equals 1, and that checks out. And then what about c? So c is like this. 2 to the power of 4 cubed. And that's going to equal 2 to the power of, what's 3 times 4? 12. Because of the third law of exponents, which says that if you got the same base, 2, then you can actually just multiply. If you're squaring, cubing, whatever, raising an exponent to a power, you can multiply the exponent by the power it's being raised to. And I'll just, for the sake of repetition, what's another way of writing all this? 2 to the power of 4 is being cubed, so that means you're multiplying it by itself 3 times. So if I wanted to, I could write it out this way and in a much slower way. 4 plus 4 plus 4 is 12. So I've just used the first law of exponents to prove the third law of exponents. All right, number 12. Write each of the following expressions as a single power of x. In other words, basically just solve these, or simplify them. You can't really get a number answer, so it'll be simplifying rather than solving. All right, so x to the power of 10 over x to the power of 5. What do? When we divide by exponents, we're going to, if they have the same base, we're going to subtract the bottom from the top. So that's going to be x to the power of 10 minus 5 is 5. We can also do c, x to the power of 4 divided by x. I can subtract this from that, knowing that x is the same as x to the power of 1. So 4 minus 1 is 3. So x cubed is my answer. I'll just continue over here. What if I have something like x to the power of 8 raised to the 8th power? That means x to the power of 8 times x to the power of 8 times x to the power of 8, 8 times in total. So this law, number 3, says I can multiply these powers. 8 times 8 is 64. X to the power of 64. That's pretty big. Okay. Let's move on to number 13. Cutting through this lesson pretty quickly. Okay, number 13. Find x in each of the following equations. A is like this. 10 to the power of 12 over 10 to the power of 4 equals 10 to the power of x. So what is x? Well, what is 12 minus 4? That would be 8. So in this problem, x equals 8. Because 10 to the power of 12 divided by 10 to the power of 4 would be 10 to the power of 8. Okay, let's do this one, e. E is a little scary looking, but it's actually not that bad. Remember, you don't have to solve these, you just have to figure out what x is. All right, and in the top, it's raised to the power of 4. In the bottom, we have an x. And then we just have no power specified here. What do we do with this? Well, what is the power of negative 8 in terms of negative 8? Well, that would be to the power of 1. And this looks a little different from this only because it's not got parentheses. If I wanted to, I could stick parentheses on and then add that 1 right there. So if you're dividing exponents and thus subtracting this power from this one, then 4 minus what is going to equal 1? That would be 3. So then x equals 3 because 4 minus 3 equals 1. Number 14. Use the table of powers of 3 at the right to find the following products or quotients. So I'm just going to write some of the table. And I'm going to change the problem so you don't need more than this of the table. But we could do something like this. 3 to the power of 1 cubed. But what would that be? Multiply 1 times 3. That's 3 cubed. And what does that equal? 27. 3 cubed is 27. So that's my answer. Or what if instead I had 3 squared, and then I squared that. 2 times 2 is 4. So 3 to the power of 4, which equals 81. So that's all you're doing with these problems. Let's look at 15. Find each of the following quotients. Okay, this is a little bit more complex. All right, so what do we have here that's new? Here we've got a total of 3 different bases, 8, 2, and 10. So can I subtract the powers of 8 and 2 from each other? No. But can I subtract the powers of 10 and 10 from each other? Yes, because they have the same base. So I'll just deal with these two first. What's 8 divided by 2? That's 4. Times 10 to the power of 8 divided by 10 to the power of 2. So subtract 2 from 8 using that second law of exponents. And so what's 8 minus 2? 6. So that's my answer, because I can just keep it in scientific notation for this lesson. 4 times 10 to the power of 6. We'll do another like that. Let's do F. This one's a little tricky. 7 times 10 to the power of 12 over 50. Well, there's an easy way to do this and the hard way. I'm going to do it the easy way, which is to take 50 and put it in scientific notation. So that becomes, I'm just going to draw a little arrow over here because I ran out of space, 7 times 10 to the power of 12 over, what's 50 in scientific notation? That's going to be 5 times 10 to the power of 1. Now, do I have something I can work with? Yes. All right, so what's 7 divided by 5? Well, I'll do that up here, I suppose. 5 goes into 7 one time. Bring down a 0. 1.4. So that's going to be 1.4. Is that part in scientific notation? Yes, it's good. Times 10 to the power of what's 12 minus 1? That's going to be 11. So 1.4 times 10 to the power of 11 is my answer. And number 16, almost done. There are 17 in total. All right, a swarm of locusts, once seen flying across the Red Sea, was estimated to have consisted of 250 billion insects and have covered an area of 2,000 square miles. My goodness. Write each of these numbers in decimal form. So first of all, we have 250 billion. Millions, thousands, hundreds. So just to double check, hundreds, thousands, millions, billions, 250 billion. And then the other number was 2,000 square miles. So I'm going to write, and I'll put a decimal there. 2,000 decimal miles squared. All right, now they want you to write each of these numbers in scientific notation. All right, what's 250 billion in scientific notation? We make it 2.5 and then count how many decimal places we have to move to get it all the way from there to there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 10 to the power of 11. And what's 2,000? Well, that would be 2 times 1, 2, 3, 3 places, so 10 to the power of 3. Now C, it says approximately how many locusts were there in each square mile of swarm? Well, what we could do is if there were 250 billion and 2,000 square miles, then what we can do is we can divide 250 billion by 2,000, and that'll tell us how many there were in each square mile. So I can divide this by this. All right, so I'll do some long division here. 2.5 divided by 2, so I got that. Need more space. I get 0.5. I'll add a decimal up here. 2 goes into 5 twice. It's going to be 10. 2 goes into 10 5 times. So I get 1.25 times, now I deal with the tens. All right, so 10 to the power of what's 11 minus 3? 8. So there are 1.25 times 10 to the 8th locusts in every square mile. All right, last one in this lesson, number 17. The sun contains about, oh my goodness, 1 times 10 to the power of 57 atoms. That's a lot of atoms in the sun. The volume of the sun is about 8.5 times 10 to the 31st cubic inches. How many atoms on average are in each cubic inch of the sun? Round your answer to the nearest tenth. Okay, well, I'm glad they're letting us round. So let's take a look at this. If I were to try to figure this out, there's this many atoms divided by this amount of space. So in other words, that many atoms is spread out into this amount of space. So I'm going to go 1 times 10 to the 57th divided by 8.5 times 10 to the 31st. I'll save us some trouble and let you know that when you divide 1 by 8.5, you get 0.1176. And that's going to be times 10 to the power of what's 57 minus 31? 26. Now it says to round to the nearest tenth, and so I'm not going to do that yet. I'm going to do that after I put it in scientific notation. So to put it in scientific notation, I need to have the decimal to the right of my first non-zero digit. So that would be 1.176 times 10 to the power of, well, I just multiplied it by 10 to make it, instead of 0.1, 1 point. And so to do that, I had to borrow one of these 10s. So instead of 10 to the power of 26, it'll be 10 to the power of 25. And I would be done here, except that it wants me to round to the nearest tenth. So ones, tens, nearest tenth. Is this number 5 or higher? Yes. So that means I'm going to round up. So my final answer is going to be 1 point rounded up to 2 times 10 to the power of 25. Thanks for watching. Hope you found this video helpful. God bless, and have a good time studying. Take care.